or abelian varieties. And these were higher dimensional varieties, but somehow one had more of a handle on them because they classified geometric objects. And so we sort of, our first step in tackling Falting's theorem or Mordel's conjecture was to reduce the question about rational points on a single curve to a question about the collection of curves which really corresponded to some points on some higher dimensional moduli space. So, motivated by that, one could ask a question of maybe understanding, one could ask about the curves, since this is a lecture series about curves, which are also moduli spaces. So, and maybe try to obtain finer Diophantine results about those curves. So, that's sort of the motivation. So the question I want to ask is, what can one say? Well, first thing, what curves are also moduli spaces? Sort of classifying natural geometric objects, and the most basic kind would be moduli spaces of curves. And the answer, well, the most basic examples of curves which also are moduli spaces are the so-called modular curves, which classify elliptic curves, possibly with some extra structure. So we're going to discuss today modular curves. Now, so the most basic example is the moduli space of elliptic curves. Which, well, as a scheme over Z where I invert 2 and 3. So let me say over spec of Z 1 over 6 is equal to the spec of Z 1 over 6 adjoined J. So J is the so-called J invariant of the elliptic curves. So we know that elliptic curves are classified by their J invariants. And so morphisms of this ring into any Z of 1 over 6 algebra are essentially in bijection with isomorphism classes of elliptic curves over this base. Okay, that's not quite true because there's a technical problem with automorphisms of the underlying curves. So if I really want to write something correct down, I have to kind of qualify that by saying this is actually coarse moduli spaces. There's a technical issue which is not very important. So I'm going to, okay, but so this is essentially, well, this is the affine line, this variety classifying elliptic curves. So from a Diophantine point of view, it's not so interesting. So to make the question more challenging, one adjoins auxiliary level structure to get curves of higher genus. So I'm going to fix a prime P greater or equal to 5. And when I'm going to consider the curve which is denoted usually y1 of P. So this is the moduli space, or it's the curve over spec Z. So I'll tell you what, well, so here I'm going to let Z be the ring Z of 1 over P. So the ring where I invert the prime P. So the curve over spec Z, classifying pairs consisting of an elliptic curve, E, together with a point of order P. So where E is an elliptic curve and capital P is a point of order P on E. So So what this means is that if I let R be any Z algebra, then the points on Y1 of P with values in R is identified with the set of pairs up to isomorphism, so the set of isomorphism classes of such pairs over the ring R. So this up to isomorphism over the base, or isomorphism. Okay, so it's a fact that this moduli problem is representable by a scheme, and so that this set is in bijection, natural bijection, with the R point. So this is the curve I'm defining to be Y1 of P. Now, you can actually write down equations for these curves, but that's not a very useful way of working with them. I mean, it's really better to work directly with the fact that one has a kind of explicit understanding and control of the points on the curve via this interpretation, via the definition as a solution to a moduli problem. So I'm going to also have a use for the curves y0 of P, so which are just quotients of this by certain automorphisms. So there's a natural operation, there's a natural action of Z mod PZ star on this on the curve y1 of P, where an element here would send a pair E, so alpha in Z mod PZ star would send a pair E comma P to E comma alpha P. And so I just define y0 of P to be the quotient of this curve y1 of P by the action of this group. Oh, when I say up to R isomorphism? Yeah, I mean the obvious thing. I mean an isomorphism between the underlying curves, which sends one fixed point to the other, right? So it's the natural, what you would expect. Okay. So the fact, which is that y1 of P and y0 of P are smooth over spec Z. So there are even models of these curves over the spectrum of Z, sort of canonical nice models, which have singular fibers above the prime P. I'm not going to have any use for the bad reduction properties of these curves. I'm just going to work over this base. When then these curves have good reduction, everywhere good reduction. Okay. So, okay. So the basic theorem which I want to discuss in this lecture is the following theorem of Mazur, which classifies the rational points on the modular curve y1 of P. And so the theorem is that if P is a prime, which is either 11 or greater than 13, then the set of rational points, well, so it's not just finite, which we already know from, well, I mean, so it's not hard. Actually, maybe I should give this to you as an exercise, or, well, compute the genus. This will, actually, you don't maybe of of y0 of P and y1 of P. So you might want to think about that. I mean, we'll see later some facts about these curves, which will give you some handle. I mean, you obviously want to try to understand these curves as ramified coverings of the projective line and use Riemann-Hurwitz, and we'll see later. So anyway, if you compute the genus, you see that very quickly, well, certainly for this range of P, the genus of the curve is strictly greater than 1. So Faltings tells us that this is a finite set, but in fact, we can say much more. This is actually empty. There are no rational points on y1 of P over. Yeah. So that's what I want to prove today, and I want to make the remark now that this is a result about curves. So this is a theorem about curves for two, or in two different ways, I guess, in two different ways. Okay. So the first way, which is the one that I've been kind of hinting at now, is that it sort of tells you something very precise. So it says something about the infinite collection of curves y1 of p as p varies, and says that if p is large enough, then this set of rational points is empty. And so these are curves of genus bigger than 1. But it also says something about elliptic curves. Okay? So it also implies that the torsion on elliptic curves is uniformly bounded. Okay, so that any elliptic curve over the rationals. So it also implies that torsion on all elliptic curves over Q is uniformly bounded. So no elliptic curve over the rationals can have a point of order of prime order p greater than 13. Okay, it's uniformly bounded. Yes. Oh yeah. So of course one could try to get a sort of a more precise result with all integers, and Mazur actually does that. I mean, one has now classifications of all. When certainly. Let's see. Yeah, I mean, one can reduce, so you're thinking about the problem of bounding the torsion, for example, right? One can essentially reduce the problem to the study of these curves, y1 of p. So the key problem is to bound the primes. So now we know that in the torsion subgroup, the only primes that can appear are in a finite list. And then you can kind of study one by one the small set of curves, you know, in y1 of n, where n is only a product of these primes, and show that at certain points they have no rational points. But that's a sort of a simpler problem because you're only dealing with a finite collection of curves. And in fact, those things were done before Mazur by Ogg and others. I mean, so one had a complete classification. So this sort of result led to a complete classification. So there's a more precise result of Mazur, which says that which gives a precise list of all the possible torsion subgroups of elliptic curves that can arise. But this is really the essential ingredient in that result.
What about is there any attempt to generalize this to quaternion number fields, or is it
So that's a good question. So you're going to see today in my lecture that the techniques I'm going to describe are very much tied to Q, to the rationals, unlike what I discussed yesterday and the day before with faultings, where in fact one proved the result for number fields and one really had to work. I mean, it was much easier, in fact, to get the result very generally over number fields. So the techniques I'm going to describe now look like they're very connected to the rationals, but you'll see this afternoon there's going to be a lecture by Marussia Reboledo, who's going to discuss a generalization of these two number fields. It's a very beautiful result of Mirel, which says something about the torsion of elliptic curves over arbitrary number fields and gives very strong boundedness conjectures there. But strictly greater than 1, yes. I mean, the genus of these curves is growing, and if I'm not mistaken, they're always bigger than. I'm looking at y1, not y0. Okay.
What is the timeline of this theorem versus Faulting's theorem?
Okay, that's a good question. This was done before Faulting's theorem. Okay. I think it was done roughly in. It was before I was around. I think in the late 70s, maybe 79 or so. 78, I think. 78, 79.
77,
yeah. So it was in the mid-70s, around 75, that these ideas appeared, whereas Faulting's proof was roughly in 85. So it was about 10 years later. It was around 75, whereas Faulting's was around 85. Now, I want to emphasize that both results are really different, even in the context of modular curves. These are different results. But what we're doing here is we're looking at a collection of curves, namely all the modular curves as p varies. We're fixing the field, in this case the rationals, and showing that there are no points after a certain stage on these curves. Whereas, in some sense, Faulting's is better at fixing a curve and then varying the field. And we know that for every field, there are finitely many points. Now, in particular, what we'll see today is that the methods that I'm going to describe of Mazur do not imply, and even the ones that we'll see this afternoon that Marussia is going to explain, do not imply that any given modular curve is Mordelic. See, this is an interesting question. I mean, when one doesn't have a way somehow of dealing, I mean, so of getting faulting theorem, even for a single modular curve for using these techniques. Okay? Yeah? Sorry, can you speak louder? I can't hear you. I'm sorry, I really can't hear you. You have to speak much louder. You're just too far. Yes. Yes. Oh, you mean why this, what I've said here, implies or is related to this one? Well, because you see, rational points on y1 of p correspond to pairs consisting of an elliptic curve over the rationals and a point of order p defined over the rationals. That's the moduli. So, yeah, I mean, that's what the moduli. I mean, when I say EP over R, I mean that the point p is also defined over R. So we put R equals Q. No, so it does, but I haven't exactly explained how. You have to do a little bit more work. I mean, but it was work that was prior to that about classifying points on small modular curves. So that's just a small technical point. I mean, it's not logically a consequence, but in fact, it is. You know, with okay, so. Okay, so now I want to kind of explain some of the ideas that go into this proof, and. We have to first talk about certain compactifications of these modular curves. So these are open curves. I mean, they're affine curves owing to the fact that there are certain degenerate elliptic curves, and then one wants to kind of add them to the moduli problem in order to get a nice projective curve. And these are, so when I join certain cusps, oh, maybe before I say this, I wanted to say first thing, I mean, to make this a little bit concrete, I want to give you a description of these curves over the complex numbers, okay, over C. So if we look at the set of complex points on y1 of p, so by this general moduli description, this corresponds to pairs consisting of an elliptic curve and a point of order p over the complex numbers up to isomorphism. And one can show that this is identified with the quotient of the upper half plane by the action of a certain subgroup of SL2Z by Mobius transformations. And here, gamma 1 of p denotes the set of 2 by 2 matrices with entries in Z with C congruent to 0 mod p and A and D congruent to 1 mod p. And the identification, which I leave to you as an exercise, I mean to show that, is just to any tau in this upper half plane, you associate the pair consisting of the complex torus C modulo 1 tau. You take the lattice by 1 in tau, and that's an elliptic curve with the complex numbers by Weierstrass theory. And then you take the point 1 over p, 1 over the prime p. So that's the point of order p on this elliptic curve. This is a description of a C, and so this establishes the bijection, which is an analytic isomorphism between this Riemann surface and that one. Okay, and then likewise we have an identification of y naught of p with h modulo gamma naught of p, where gamma naught of p is the same thing, but we don't require that we have the same kind of group. We just look at the matrices, which are upper triangular modulo p. So these are all subgroups of the 2 by 2 matrices with integer coefficients, SL2Z, and the action on H is by Mobius transformations. Okay, so we have a fairly concrete understanding of what this curve looks like analytically as a complex curve it's a quotient of H by one of these very specific subgroups. Okay, so I want to now discuss some things about compactification. So it's customary to compactify these curves by joining to them a finite set of cusps. And so I'm going to let x naught of p, I only have a use for this one actually, so be the compactification of y naught of p obtained by adjoining certain cusps. So as a complex curve, over the complex numbers, this process just consists of augmenting the upper half plane by adding to it the points in P1 of Q, which you think of as sort of living on the boundary of the upper half plane, and then looking at gamma naught of P orbits. Now, there are actually, if you look at the action of this group on the set of rational points, you actually have two orbits. So this can also be... Oh, sorry, yes, union H. Yeah, so I've added this to the 2H, yeah. So this I can also write as H mod gamma naught of P union two orbits. So they have the orbit of 0 and the orbit of infinity. It's not hard to check that those are exactly the two distinct orbits of P1 of Q under the action of gamma naught of P. Of course, to make this precise, in the category of Riemann surfaces, one has to describe the analytic structure in the neighborhood of 0 and infinity, and one can do that. One has to kind of describe a local parameter at infinity. And yeah, so that's sort of what it looks like over C. But now I want to also work algebraically with this. I'm going to need to work algebraically with this curve in a neighborhood of infinity. And so a local parameter at infinity. So I'm going to look at sort of the behavior at this cusp, infinity. So this is given by considering the Tate curve. So I'm looking at this infinity, this point as a point over spec z. So in other words, a section of this curve over spec z. So the local parameter is given by q, which is which analytically is e to the 2 pi I tau. But you can understand this algebraically by considering the following elliptic curve, which is called the Tate curve. So this is just the elliptic curve z double bracket q star modulo the group generated by powers of q. So this is actually a curve over spec z. I've given here an analytic description, but if you look at functions on this ring which are invariant under multiplication by q, you get two basic ones and they satisfy a cubic equation. And the discriminant of this curve, so this is defined over the scheme z of double bracket q. It's an elliptic curve over z double bracket q. Its discriminant is q times the product of 1 minus q to the n to the power 24. So this is actually, so it's an elliptic curve over z of double bracket q where I've inverted q. So this E Tate, is an elliptic curve over z double bracket q adjoined 1 over q. And so this q is, so I think of q equals 0 as corresponding to this extra point, which I've added, which corresponds to an elliptic curve with kind of degenerate reduction. And so this q gives you a parameter for a formal neighborhood of that added point in the modular curve x naught of p. Okay, so
what do you mean by this power series ring over spec z?
So, okay, so this, sorry, I mean, spec z of, so this is an elliptic curve, yeah, I guess I should say spec z of q. So it's an elliptic curve over this, spec z of q1 over q. That's what I mean, this, yeah, exactly. So it's smooth. I mean, you see, its discriminant is this, which is invertible there. I mean, so yeah, as long as you can invert Q, you're fine. So this. No. So I've compactified the moduli space, but the extra point I've added corresponds sort of to Q equals 0, which corresponds to a curve of degenerate reduction. So I've kind of added this point corresponding to the degenerate elliptic curve, but in a formal neighborhood of this. So this is like a punctured formal neighborhood. The point that I'm filling in corresponds to Q equals 0, which here I've inverted. Okay, so
this says you know double bracket Q star, it's Z double bracket Q points of this curve.
yes, exactly.
You have the, let's say, the Tate field, that's enough.
Yeah, so this is the multiplicative group modulo Q to the Z over this ring, right? Yeah. So if you write down, I mean, you just take, you write down functions on Z of double bracket Q star, which are invariant under translation by Q. You kind of write down sort of analogs of elliptic functions. Then they satisfy a cubic relation, and that's the Tate curve. So that's sort of. Yes, this one here. I mean, this Q. Yeah, so this I should emphasize is not an algebraic description; it's an analytic description, right? Then you have to. It's like writing down the elliptic curve over C as C modulo lattice. So this is analogous, but it's a formal description. I mean, it's an analytic description of the formal neighborhood of x naught of P in a neighborhood of this cusp. Okay, so I just want to now mention the Q expansion principle, which identifies the local, so Q expansion principle, which identifies the completion of the local ring of this modular curve x naught of P at infinity. So I take the completion at this point, and this is identified as in the formal neighborhood over spec Z with the power series ring Z double bracket Q. Okay, if you want, you can take that as a definition of the formal neighborhood. This point that I've added. So this gives me the structure of the curve near infinity. Okay. So I want to now state a criterion which is due to Mazur, which allows us to check whether the curve x naught of P or y or y naught of or x1 of P has rational points or not. And this criterion depends on the notion of a formal immersion of one scheme into another. So let me state that. So a morphism of curves J from, say, or varieties, I mean x to y, is called a formal immersion at a point x. So x here I take as a point of x of z. So I'm working with schemes over z. So I take a point in x of z. And I say that it's a formal immersion if it induces a surjection on the completed local rings at the points. So if J star, the pullback map, induces a surjection between OYY hat and OX little x hat, is a surjection where here little y is just, of course, the image of x under J. This is the definition of a formal immersion. And so it sort of captures the idea that the map should be injective in a formal neighborhood of x. So in a formal neighborhood of x, the map J should be injective. At the level of local rings, it translates into a surjection of the local rings. Now I'm going to state Mazur's criterion, which is the basis for his study of the Diophantine properties of these modular curves. So the theorem is the following. Suppose there is a quotient well, J sharp, which I'll denote by J sharp of P, of the abelian variety J naught of P. So, I mean, the criterion is going to be based on the Jacobian. So, J naught of P here is just the Jacobian of the modular curve X naught of P, this completed modular curve. So the criterion is going to be phrased in terms of a certain property of this Jacobian. In fact, this Jacobian is going to be somehow the main actor in Mazur's proof. So suppose there is a quotient, J sharp of this Jacobian, with the property that, well, so there are two things. The first is that I need to consider the map little j sharp, which consists of the curve X naught of P, embedding it in its Jacobian. And the embedding I take of the Jacobian is gotten by sending a point x to the class of the divisor x minus infinity. So I take that particular embedding where infinity corresponds to this cusp, whose formal neighborhood I described above. Okay? So that this, and then I follow that by the natural projection onto this abelian variety quotient J sharp of P. Okay? So that's my map J lower sharp. So so that I want that to be a formal immersion at the point infinity, at the cusp infinity. Yeah. This is an abelian variety quotient. Abelian variety quotient. So it might be an elliptic curve, or it might have some elliptic curves in it, but it will be a higher dimensional abelian variety. So what is it? So here I'm just taking some quotient, but of course in the category of abelian varieties of this thing. And I require that if I embed my curve in the Jacobian and I follow by projection onto this factor of the Jacobian, the composite map should be a formal immersion at the point infinity. Okay?
In the definition of formal immersion, do you require that map to be a continuous projection?
Just a morphism of curves is fine, I guess. I mean, you might... yeah, I mean, you kind of, it's really only makes, it's really only meaningful for finite to one, right, morphisms. I mean, yeah. I mean, you could still write it down, but it wouldn't make much sense in that. It wouldn't, yeah. So the second thing, the second crucial property you want about this quotient is that it has finitely many rational points. So the Mordell-Weil group of this J sharp of P should be finite. And if those two conditions are satisfied, then the conclusion is that y1 of P is empty. Yeah. I shall raise it all the way up to here. Is that good? So that's the statement of the finiteness criterion of Mazur. y1. y1. So there's an interplay between these two curves. Okay, I have a condition involving x naught and j naught, but I'm then making a diaphanting conclusion about this larger curve x1 or y1, which kind of sits above but is related by an unramified covering. And from what I said in my first lecture, it shouldn't be surprising that, of course, there's a relation between these various diaphanting problems. This is I mean, I'm interested in this because I'm interested in classifying points of order P, but I'm going to study the curve in some sense which classifies the curves with a subgroup of order P. That's going to be enough. So let me give you a sketch of the arguments. And, yeah. So let x tilde be some point in y1 of P defined over the rationals. I'm going to start with a rational point x tilde, and I want to prove to you that eventually that this rational point is actually, well, that it's not there. I mean, it can't exist. I'm going to get a contradiction from that. So I'm going to let the E, comma, capital P be the corresponding point, which is classified, which corresponds to this x tilde. So the first thing we observe is that this elliptic curve E has potentially multiplicative reduction at the prime 3. I'm going to work with the prime 3. I mean, P is bigger than 3, so this curve has a good reduction. The curve y1 of P has good reduction outside 3. But I have this elliptic curve, which corresponds to a point on this curve. And what I'm saying is that this elliptic curve has to have some kind of bad reduction. It has to have multiplicative reduction. It cannot have good reduction. And why is that? Well, it's because of the presence of this rational point of order P on the curve, which is forcing it to. So why? Otherwise, so I can consider the narrow model of E and then look at its special fiber, which is an abelian scheme or a semi-abelian scheme over F3. And then, so if this had good reduction, this would be an elliptic curve. So this is either an elliptic curve or, in the case of additive reduction, I mean, this is or an extension of a finite group of connected components, so a finite group, capital Phi, of cardinality 2 to the A, 3 to the B, by the additive group, GA. In either case, if it's an elliptic curve, the number of points over F3 is bounded by the Hasse bound. It's at most 5, I guess. I mean, there can't be more than 5 points on the elliptic curve. And since P is supposed to be larger than 5, then this cannot contain a point of order P. Even less in this case, since the additive group over F3 has cardinality 3. So the only way that the elliptic curve can contain a point of order P is if it has potentially multiplicative reduction. Okay, so here I've used a little bit about the theory of reductions of elliptic curves, and so for those who aren't familiar with that, don't worry too much. The main point that you should take from this first step in the argument is that we're kind of understanding a property of this point x tilde, or rather of its image in, of this point x tilde. We're understanding some feature of that point in terms of the moduli description. So we know enough about elliptic curves and their bad reductions and so on to make some conclusion about how this point is behaving locally at this prime 3.
So we suppose P is prime
3. And P is big. P is bigger than 13. Yeah. In my result, I guess the criterion is, I'm supposing that P is bigger than 13. I have a point of order P in the generic fiber, okay? And so in the special fiber, it'll still, because it's a point, it's a P torsion point, and the P torsion injects in the P torsion on the special fiber at 3, because P is prime to 3, for example. Always for these narrow models. I mean, again, that's a little bit. I mean, don't worry about this. If you're not comfortable with this more, the case of additive reduction, don't worry about it too much. I mean, there's enough technique that we have concerning elliptic curves to deal with the additive reduction case as well. But, so then the second step is to consider the image of this curve, of this point x tilde in x naught of P. So be the image of x tilde in the curve x naught of P. So then, what this first part is saying geometrically is that x reduces to either the cusp 0 or the cusp infinity modulo 3. So in the special fiber above the prime 3, it specializes either to one of these added points which correspond to elliptic curves with degenerate reduction, with multiplicative reduction. So we can assume, without loss of generality, that x over f3, so I look at the special fiber, I mean the restriction of x in the special fiber above 3 is equal to infinity over f3. So why can I do that? Well, if it reduces to 0, I can take the moduli pair corresponding to x is the elliptic curve E together with the subgroup of order p generated by this point capital P. And I can replace that by the quotient E mod p. And then I take the full p torsion in E modulo the group generated by p. And this kind of correspondence gives me an involution on the curve x naught of p, which interchanges the cusp 0 and infinity. So if your point reduces to 0, you can always get it to reduce to infinity by applying to it this involution. Okay, so finally, so then step 3 in the argument is we consider the image of the divisor x minus infinity under the morphism which I called, or maybe actually, so let me call this map here, this projection map, let me call it phi sharp. Okay, so J sharp is the composition of the embedding in the Jacobian with phi sharp. And so I consider the image of this degree 0 divisor under phi sharp. And what I find is that this image belongs to the connected component of the identity of J sharp. So if I look at J sharp of P over Q3, it belongs to the connected component of the identity. It reduces to the identity modulo on the special fiber. Okay? That's because x was specializing to infinity modulo 3. So I have that. And by assumption, of course, it also belongs, since this is a rational divisor, it also belongs to J sharp of P of Q, to the rational points of J sharp of P. But now, this one?
No, the lower one.
The lower one? Okay. Actually, this one is. This. Okay, it is okay? Can you see? Yeah? Okay, so we have that. It belongs to this connected component of identity and to the rational points. But this is torsion free. It's identified with the formal group of this abelian variety in characteristic 3. So it's a torsion-free group. And this one is torsion by assumption, because I'm assuming that the Mordell-Weil group of this quotient is finite over the rationals. And therefore, this image has to be 0. Phi sharp of x minus infinity is equal to 0.
Can you explain or say one more time why J sharp 1 of P Q3 has to be torsion free?
Because of the formal group. This is identified with the formal group of this abelian variety over Q3. Right? It's the kernel of the reduction mod 3. So you have an exact sequence which sends the points over Q3 to the points over F3. And this is the kernel of this map, which is torsion-free because it's identified with the formal group. Yeah. So we have this. So therefore, J lower star of x, of this point x, is equal to the origin, to the identity in this abelian variety quotient. So now we're going to use the formal immersion property. So at this stage, what I've used is the fact that the J sharp of P has finite Mordell-Weil group, crucially to know that this was torsion and therefore that this is the identity. And now I'm going to use the the formal immersion property to conclude the proof. So okay.
Why couldn't you repeat the last argument to replace x by just a irrational point? Without going into
But here x, yeah, x could be any rational point. So you mean why do I work with y1 and not with x naught? At this stage of the argument, there's no need. I could have also worked with. No, well, the only point where you see, no, it is in this step 2. Sorry, in step 1. When I look at the moduli point corresponding to this x, I said that it had multiplicative reduction because the elliptic curve was endowed with a point of order p. So if I started with a rational point on x naught, I would have an elliptic curve endowed with a subgroup of order p, rational, and that wouldn't allow me to conclude. For example, the curve could have Cm by an order in imaginary field class number 1. So I wouldn't be able to conclude that this has to meet infinity over the special fibers associated with small primes. So it was in step 1 that I kind of exploited the interplay between x1 and y x naught.
So here Q3 you may replace by a.
Yes, 3 is just the smallest prime that will happen to be handy. I could have taken me.
Where do you use the 3 small?
No. I mean, I need a small prime because I want to show that the philosophy is that if you have an elliptic curve with a point of order p and p is large, that elliptic curve is going to have bad reduction, in fact, multiplicative reduction, at all the small primes that are small enough. So I'm just working with 3.
But torsion 3 you use the decay multiplication.
No, here I'm in the formal group of some abelian variety in characteristic 3 over Q3, and I know that formal group is torsion free. This is a general fact. But I mean, I use the fact that these meet over F3 to know that this maps not to J, not just to a Q3 point, but I have this 1 here, right? This 1 means that I'm congruent, I specialize to the identity. So, I mean, maybe I should write this down. I mean, I have an exact sequence, J sharp of P of Q3. This is an abelian variety, so it maps to J sharp, it's a projective variety, so it maps to J sharp of P over F3, which is some big group. I mean, that could certainly have plenty of points of large order. I mean, I don't have any control over the dimension of this abelian variety, for example. And the kernel is this J1 sharp of P. And it's the kernel which is torsion free. Okay. So I need to know that I'm in the kernel too. Okay, so let's now complete the proof. So the formal immersion property J sharp. Yes, I mean this whole. You see, this curve has good reduction over spec z. So does this abelian variety, and the embedding here is also defined over spec z. And this quotient is going to be defined over. So everything is defined over spec z, where I've only inverted p, and it's smooth over spec z. 1 over p. No, that was just at the very beginning when I wanted to be sloppy in writing down. But if you work a little bit harder, you can write a good smooth model over. Yeah. Okay. So the formal immersion property now tells us something. I claim that it implies that necessarily x has to be equal to infinity. The point x on x naught of p has to be equal to infinity. Why is that? Well, so let me give myself an affine neighborhood, spec R, be an affine neighborhood of the point x. Then this point x corresponds to a homomorphism from R, and I want to think about this point threadically, as a threadic point, So it gives rise to a homomorphism from R to Z3. Now, because X is mod 3 is specializes to infinity, this morphism factors through the formal completion. Let's see what. Yeah, I mean this completed local ring, which I mentioned before, O x naught of p infinity, which is identified with Z double bracket Q. So it factors through this formal completion. In other words, it corresponds to evaluating these power series by specializing Q to some three-adic integer, which is, the power series has to converge, so this Q is divisible by 3. Okay, that corresponds, that's because X is multiplicative. It corresponds to a point with multiplicative reduction. Now, the formal, what we've shown in step 3, what we've shown is that this map X composed with J sharp star is equal to infinity composed with J sharp star. So, of course, we also have a map infinity from Z double bracket Q to Z3, which is just taking the leading term, specializing at Q equals 0. That corresponds, taking Q equals 0, corresponds to the point infinity on the modular curve. And these compositions are the same because they correspond to the points here that are the images of X and infinity. But these maps, this J sharp star is surjective by the formal immersion property. So that implies that X is equal to infinity since J sharp star is surjective. So geometrically, we have 2 points on x naught of p which are in a formal neighborhood of infinity. We've shown that they map to the same thing. And since the map is injective on the formal neighborhood, that's the formal immersion, then the points have to be the same. Okay, so that's the end of the proof. And the problem now is to construct a good quotient. So the problem is to now construct a good quotient J sharp of p of the abelian variety J naught of p, satisfying these 2 conditions, that the Mordell-Weil group is finite and the map is a formal immersion. So, so that kind of brings me to the next part of my talk, which is sort of the study of the Jacobian. So what we're using here is a sort of very natural strategy for studying rational points on a curve, which is to embed the curve in its Jacobian, and then hope that the Jacobian maybe has finite Mordell-Weil group, or at least has a quotient with finite Mordell-Weil group, and then obviously that's going to give you some tight control on the set of rational points. Yeah. Do you have?
What is the affine neighborhood of X after infinity?
Oh, let me say it does contain infinity. Okay. Yeah. So it. I don't have X infinity. I see. I mean, X and infinity are even contained in the same formal neighborhoods. So if you want, you could take R to be Z double bracket Q. I mean, maybe, in fact, maybe I should have done that. I mean. Okay. So the second part now is to try to control the Jacobian J naught of p. So this is sort of part 2 of my talk, controlling J naught of p. So how can we control this abelian variety and produce a quotient with finite Mordell-Weil group? And the key ingredient here is the connection between J0 of p and modular forms. And this is a theme that I'll be also, I'm actually running a little bit late, so I might not have time to say as much as I wanted to today, but this is a theme that we'll be developing also tomorrow when I talk about Fermat's theorem, and also in the course of next week when we talk about elliptic curves and the Shimura-Taniyama conjecture. So I just want to sort of be kind of brief at this stage, in this second part. So what is a modular form? Okay, so definition. Well, okay, so we want to understand this abelian variety. In particular, we would like to understand its endomorphism ring and how it acts and so on. And we try to use the endomorphism ring to break up J naught of P into irreducible pieces. In order to a useful thing to understand an abelian variety is to look at its tangent space. In other words, the space of differentials on the abelian variety, which corresponds to the space of holomorphic or regular differentials on the curve. So we define, so I'm going to define S2 PR to be the space of regular differentials on the curve x naught of P over the ring R, where R is an easy algebra. So this S2 of PR is called the space of modular forms of weight 2 on gamma naught of P. So, or of level P and weight 2. Now, why is that? Where does this terminology come from? Well, if you look at this definition in the complex setting, so if you look at differentials on the modular curve defined over the complex numbers, then these can be identified with functions f from the upper half plane to C, which are holomorphic, and with the property that f of z dz is invariant under the natural action of gamma naught of P by Mobius transformations. Okay? And moreover, well, we want plus a condition of being holomorphic at infinity. Okay, so this takes care of holomorphic on y naught of P. And what does it mean to be holomorphic at infinity? Well, if you take this differential and you expand it in terms of the local coordinate at infinity, namely this parameter q, which in the complex description is just e to the 2 pi I tau, then you should recover a holomorphic differential. In other words, a differential which can be written as a power series in q times dq. Okay, so the condition then becomes that if I take f of tau, I can write it as a sum an q to the n, where q is e to the 2 pi I tau. That's my local coordinate. So I want this times dq, where the expansion could go from 0 to infinity. So I want to have a power series here. That's what it means to be regular. We like our modular forms to start with 1, and so we write it like that. dq over q in some sense is a sort of, this is a better way of writing it. So we want that this expression, this power series, is called the q expansion of the modular form, and so we require that this holomorphic function have an expansion in powers of q with whose leading term is 1. Is it? What is it? Yeah, and also at 0, you're right. Plus, at infinity and 0, you're completely right. Okay. And for holomorphicity at 0, you do the same thing, but you translate by some matrix from 0 to infinity. So there's a sort of a concrete description in terms of certain kind of holomorphic functions of the space of modular forms on gamma naught of P of weight 2 and level P. Okay, I guess I have to cut to the chase. I'm going to just state a result, which I'll explain further tomorrow and a little bit also on the lecture of Monday when I talk about elliptic curves, which is a sort of basic decomposition of the Jacobian J naught of P as a direct sum of so we have a sort of decomposition. So actually, I think, okay, what I'll do maybe now, I just have too many things I want to say. I'm running a bit late. So I think what I'll do is maybe I'll break here. And where is Marussia here? Yes. So what I'll do is maybe I'll, instead of your talk, I'll kind of try to finish up what I wanted to say because it's a necessary prerequisite for what you wanted to cover. And we could kind of shift things a little bit. I mean, so maybe I'll continue because I'm kind of in limbo here and I don't have time to finish. Okay? So instead of Marussia, I'll start and then we'll kind of rearrange the schedule a little bit. Okay? So I think it's better to do that. Otherwise, I'll just rush too much. Yeah. So it's not.